So in this section, we're going to dive deep into inverse trig functions. So we're used to the trig functions themselves. We've talked about inverse functions in other classes before, but the idea behind this is if you have a function and it's one-to-one, meaning that for each x value, there's a unique y value corresponding to it, you would then be able to reverse the roles. So you can swap what the input and output is. So if we think about our normal trig functions, we input an angle and then we're getting that ratio out, which is one of those sides, the comparison of sides for the triangles. For an inverse trig function, we're going to be swapping those roles. So we're going to input the ratio and then our angle is going to be the output. The problem is if you think of all of our trig functions, they're not one-to-one because they're that periodicity. So what we have to do is make a restriction so that you still get all of the same values between sine and cosine and whatever function it is, but you're not having that repetitiveness, okay? So we're going to start with the inverse cosine function because that one tends to be the easier to think about. And then we'll go through sine and tangent. And then really the other inverse trig functions follow in a similar way. But again, you always can relate these to reciprocal functions. So if we think about y equals cosine of x, it is not a one-to-one function. So what we're going to have to do is restrict its domain to find an inverse. So if you think about what the graph of that function looks like, here's our x values or our input, our y values. The cosine function is trapped between -1 and 1, and we can graph one full period between 0 and 2 pi. So this angle here would be pi over 2. This would be 3 pi over 2. The cosine function starts at 1, 0, -1, 0, +1, and then repeats from there. Then we get that nice wave shape. So if I'm going to restrict this, I want to make sure I take on every single y value, but I don't have a break in my function at all. So if we consider from 0 to pi, what's going to happen is you still get all the values between -1 and +1, but over this interval, we're going to be able to pass the horizontal line test. So if I restrict it right here, between 0 and pi, no matter how I draw a horizontal line, it's only going to hit the graph in one spot on that interval. So here between 0 and pi, we hit all of the values between -1 and 1. So we're going to restrict it to this interval. And so on the interval from 0 to pi, we're 1-to-1. We are going to be able to find the inverse of the cosine function. So we're going to draw two pictures for this. We're going to look at what the graph of cosine of x looks like, and then we're going to look at that inverse. And remember, normally when we have an inverse, we use that notation with a -1. So when I talk about the inverse function, you can represent this two ways. You can see cosine to the -1 of x to say the inverse of cosine. However, I tend to not like this particular notation, even though it is what we have for inverse, but it often gets mistaken as a power. And we know cosine squared represents something, cosine to the third. So I don't want you confusing that for 1 over cosine, which is secant. So instead, we also use arc cosine. And so you'll see you have buttons on your calculator to represent this to be able to find the inverse of the cosine, sine, tangent functions. So on this interval, we're going to start with our graph of cosine, and that's going to lead to our graph of inverse cosine. We're just going to go between 0 and pi, and we know pi over 2 is one of the quadrant angles. And then our y value is trapped between -1 and 1. So we start up here. This first point goes through 0, 1. Then it goes through pi over 2, 0. And then it goes through pi, negative 1. Okay. And then our graph of the cosine function looks like this. Okay. So the domain we restrict to be from 0 to pi. And then the range is going to be all the values from negative 1 to 1. So when I graph the inverse, remember those roles are going to switch. So all x and y values switch. So instead here, our domain is going to be from negative 1 to 1. And our range is going to be an angle from 0 to pi. Okay. So what was an x value now is going to become a y. And what was a y becomes an x. So our x is trapped between these two values and our y is trapped between 0 and pi. You then go ahead and you can do this a couple ways. Remember that graph is a reflection across y equals x, but also these flip-flop. So it goes through the point 1, 0. It goes through the point 0 pi over 2, which would be right here. And then it goes through negative 1 pi, which is up here. Okay. And then that graph still has that same fluid shape. But again, these two are reflections about the line y equals x. Kind of hard to draw because I didn't draw these to scale. But you would go ahead and you could see they're going to be the flip over this axis. Okay. So let's try getting some practice just evaluating this inverse trig function, and then we'll move on to both sine and tangent, and then do a bunch more problems with it. So we want to evaluate this exactly in radians, because again, that angle is going to be, or that output is an angle, and we want to deal with radians. Okay. So this is very hard to think of when it's in this form, just cosine inverse of root 2 over 2. So what I always like to do with these is I like to turn it into an equation that I've seen a little bit better. So remember the output of this is going to be an angle, where this angle is in the interval from 0 to pi. Okay. So instead of thinking of it this way, this is the same as solving a different trig equation. So you're asking cosine of what angle gives you root 2 over 2, where that angle is specifically between 0 and pi. Because again, there are a lot of places where cosine of theta will equal root 2 over 2, but I'm only looking for the one between 0 and pi. So you're gonna need to use your unit circle, but for the cosine function, it's going to be one of those angles in quadrant 1 or quadrant 2. And so for cosine to be positive, that tells you it has to be in quadrant 1. Root 2 over 2 is going to be that 45-degree angle. So our theta value we're searching for is going to be pi over 4. Okay. So when I'm evaluating cosine inverse of root 2 over 2, the output is the angle pi over 4, okay? So this would be how we exactly evaluate this expression. For B, same idea. I'm looking for arc cosine of negative root 3 over 2. Again, this is going to be an angle where that angle is between 0 and pi. So this is exactly the same as asking cosine of what angle is negative root 3 over 2 when this angle is specifically between 0 and pi. Okay? So if my cosine function is negative and I'm between 0 and pi, that tells me I'm going to be in quadrant 2 on that unit circle. To have cosine equal root 3 over 2, it's a reference angle of 30 degrees. So that angle over here would be going back pi over 6. So this theta value is going to be 5 pi over 6. So when I'm evaluating arc cosine of negative root 3 over 2, it's going to exactly equal 5 pi over 6. Okay. So that is our inverse cosine function. Now we're going to do the same thing for inverse sine, and realistically, tangent's going to end up following the same. The domain restrictions are going to be a little bit different here. Okay. So if I think about graphing the sine function, that one's a little bit harder. So if you think about the graph of that function, here's pi over 2 and pi strapped between 1 and negative 1. Your sine function starts at 0 and then goes to positive pi over 2. And then it would turn back around, okay? And that's a problem. I don't want these values because that would then make it so that I fail the horizontal line test. So in order for this to have an inverse, I don't want to break this up, but I need another quadrant where the sine function is going to be negative. So if you think about your unit circle, the sine function is positive here, and then I need where a sine function is negative, but it's positive in quadrant 1 and quadrant 2. So really, I'm going to take quadrant 1 and then quadrant 4 because the sine function is positive up here and negative down here. And that will give me all of those values. The only difference is I need this to be fluid, so this angle over here is going to be negative pi over 2. Okay. And so that gives me a piece of the sine function that's fully connected and hits all of the values between negative 1 and 1. So for this, we make the domain restriction from negative pi over 2 to positive pi over 2. And that gives us the full range from negative 1 to 1. So when we go to graph arc sine, those roles are going to switch. Now my x value is trapped between negative 1 and 1. And my range is going to be an angle from negative pi over 2 to positive pi over 2. So to go through these points, this one's really nice, 0, 0. When you switch those, does nothing. This point here would be negative pi over 2, negative 1. So switching that would be negative 1, negative pi over 2. Up here is pi over 2, 1. So let me label this. This is negative 1, negative pi over 2. And then switching that other point, this is 1, positive pi over 2. This one's a little bit easier to see it reflected. So if you reflect it across the line y equals x, it just flips the way that it forms that shape. So I'm going to go up and then over here. So this is our graph of the inverse sine, which again, you can denote with that negative 1, or you can write arc sine of x, okay? So let's try some examples working with this. Same idea though, you're trying to figure out what angle this works for. When the angle is positive and it's in quadrant 1, that's a little bit easier. When it's negative, again, you're gonna have to utilize that unit circle. So let's evaluate both of these. So starting out for the first one, this is going to be some angle where that angle is between negative pi over 2 and positive pi over 2. So this way I only get a single output. That's the same thing then as asking where does sine of theta equal 1 for exactly this interval. So if you think about your unit circle, here you were just looking at the right half of the unit circle. This is positive pi over 2 here. This is negative pi over 2 down here. So to have sine of theta equal 1, we are going to be right up here. So our theta value is pi over 2. So sine inverse of 1 outputs the angle pi over 2. Okay. To do the second one, same thing. This is going to export an angle, specifically where the angle is on the right half of the unit circle. So you're really asking yourself, where does sine of theta equal negative 1/2 when this angle is between negative pi over 2 and positive pi over 2? So utilizing our unit circle, we are looking at the right half here. To get that fluid motion, we're starting down here and going up to pi over 2. For sine of theta to be negative, that needs to be somewhere down here in quadrant 4. To have the output of sine be 1/2, that tells you it's a 30-degree reference angle. So that would be negative pi over 6. So the angle that makes this happen is negative pi over 6. So when we evaluate arc sine of negative 1/2, we get negative pi over 6 as an output. Okay. All right. So let's look at the inverse tangent function, and then I'll do just some kind of identities that are result for this, and we'll do a bunch more examples from there. So the inverse tangent function is honestly one of my favorite functions. It's really, really nice. So if you think about the graph of your tangent function, you do have vertical asymptotes. And that graph repeats itself. So tangent is sine over cosine. So it's undefined when cosine is 0, which happens at pi over 2 and negative pi over 2. So here I have vertical asymptotes. Let's make these nice. And then our tangent function goes through 0, 0. And then it has that nice fluid shape that goes on forever. So over this particular interval, our graph does pass the horizontal line test. So we have two vertical asymptotes at negative pi over 2 and at positive pi over 2. Your domain in this case is going to be the same as tangent or as sine, but I cannot include those endpoints because tangent's undefined there. But our range is really nice. It is going to be all real numbers. So this is our tangent function. So if I go to graph arctangent, now instead of having vertical asymptotes, I'm going to have horizontal asymptotes. My domain in this case is fantastic. I can input whatever I want, and my range is going to be an angle from negative pi over 2 to positive pi over 2. So those are vertical asymptotes now turn to horizontal. Let's go ahead and make that back to my normal tool. So now I have one horizontal asymptote of y equaling pi over 2 and a second of negative pi over 2. You still go through 0, 0, and then you end up hugging those asymptotes. This is our graph of the inverse tangent function, which again can be represented by arctan of x. Okay. All right, so let's try some examples. We're going to do one of these and then we'll look at our identities. So if I want to evaluate arctangent of 1, again, this is going to be an angle where this angle is in the interval negative pi over 2 to pi over 2. So that's the same thing as asking, where does tangent of theta equal 1 over this particular interval? So if you think back to your unit circle, in order for tangent to be 1, both sine and cosine have to be identical to each other. The only way this happens is at positive pi over 4. Because tangent is positive in that first quadrant up here. Okay? And that's where sine and cosine are the same. So that tells us arctangent of 1 is going to be the angle pi over 4. Okay. So those are our 3 main inverse trig functions. Again, if you're working with secant, cotangent, or cosecant, you really do exactly the same thing. If you're saying to find arcsecant of, say, what's a nice number, 2, this is going to give you an angle. This is asking where does secant of theta equal 2, which is the same thing as asking where does cosine of theta equal 1/2. And you use that same interval that you would for the angles as for the cosine function. So you'd be looking for where this happens in quadrant 1 or in quadrant 2. So just for time's sake, we're not going to bother with those. We really want to focus on our 3 main trig functions instead. So when we're working with these inverse functions, remember these 2 processes undo each other. So one of our properties is if you take a function and evaluate it the inverse, they cancel each other out and get you right back to where you started. And vice versa if you change this. The problem is it only works for the domain of both of those expressions. So our sine, cosine, tangent functions have domains that go on forever. So you have to be a little bit careful because the inverse trig functions have very, very, very specific outputs, okay? So it's not a problem when this is on the inside. These 2 are going to cancel each other out as long as x is in the interval from -1 to 1. Because it would make no sense to find sine inverse of 3 because there's no angle that gives you sine of theta equaling 3. If instead I have the inverse sine function on the outside, you have to be careful because sine of x has a domain of whatever it wants. So I have no problem putting in the angle 2 pi. However, for inverse sine, I can't do that. I'm not going to get 2 pi as an output. So this is only going to cancel when the inside is in the interval from negative pi over 2 to pi over 2. So really, I'm always going to tell you when you have this double combination of evaluating a sine function and its inverse or other inverse, just take it piece by piece and step by step. It's going to make your life much easier instead of just immediately canceling these things. So they don't always cancel in these instances. And even so up here, you can get tricky with it because again, if there's a 3 on the inside, sine inverse of 3 does not make sense. Because if you evaluate sine inverse of 3, it should give you an angle, but that's the same thing as asking where does sine theta equal 3. So again, doesn't cancel because that input wasn't in the original domain. Okay. And likewise then for all of these other trig functions, they are going to cancel for very specific values. So when I have cosine and cosine inverse, you're starting out with cosine inverse. So the only thing I can input into there isn't something between -1 and 1. These 2 will cancel each other out as long as this angle is in that range of the cosine inverse function. So this is only true when x is in the interval from 0 to pi. Luckily for this one, you have no problem because you can input whatever you want into the arctangent function. So this you're going to be able to cancel immediately. But when you have tan inverse on the outside, this angle needs to be in the range of the inverse tangent function. So it's only when x is in the interval from negative pi over 2 to positive pi over 2, okay? So again, I'd prefer you not utilize this at all. Instead, take it piece by piece. So for all of these examples, that's exactly what I'm going to do. So we're going to just evaluate a bunch of different things. We're going to start by evaluating cosine of cosine inverse of 1/2. Okay. So what I want to do is I want to start here on the inside. I want to figure out what does this equal. So cosine inverse of 1/2 is going to be some angle theta, where theta is in that interval from 0 to pi. So this is the same thing as asking where does cosine of theta equal 1/2 when theta is in the interval from 0 to pi. Okay. And again, this is where knowing your unit circle is super essential. For cosine of theta to equal 1/2, that tells you it's a 60-degree reference angle. Because it's positive and you're in quadrant 1 or quadrant 2, this theta value is going to be pi over 3. So the inside here is pi over 3. So I'm taking cosine of cosine inverse of 1/2. But we just figured out that that inside is pi over 3. Okay. So cosine inverse of 1/2, forgot my -1, is exactly pi over 3. And now I just need to evaluate cosine of pi over 3, and that is 1/2. So the end result of this is 1/2. Those two did end up just canceling each other out, okay? But again, only works in special cases, which is why I'm going to tell you take it piece by piece. This next one is a prime example of that. Sine inverse of sine of 3 pi over 4. So if I start with the inside here, sine of 3 pi over 4 is a 45-degree angle, so I know it's going to deal with root 2 over 2. If I think about the quadrant that that's in, 3 pi over 4 is over here, so the sine function is positive. So now evaluating sine inverse of sine of 3 pi over 4, the inside can be replaced by root 2 over 2. Okay. And this is going to give me some angle, where that angle is specifically in the interval from negative pi over 2 to pi over 2. So this is the same thing as asking where does sine of theta equal root 2 over 2 when theta is going to be in quadrant 1 or quadrant 4. And I already know the reference angle for this. It is going to be a 45-degree angle. And for sine to be positive, that is going to happen in the top half of the unit circle. So my theta output is pi over 4. Okay. So you see, I'm not going to get cancellation. The angle ends up having to change because 3 pi over 4 is in quadrant 2, and that is not an angle that can be output for my sine inverse sine function. So overall, this expression, sine inverse of sine of 3 pi over 4, actually gives us the angle pi over 4. Okay. All right, let's try one where we have a combination of trig functions. So I have tangent of arc cosine of 1/2. So again, I'm going to end up looking for the inside first. So I'm going to start by evaluating what is arc cosine of 1/2. This is going to give me an angle where this angle is between 0 and pi. That's the same thing as asking, where does cosine of theta equal half when theta is in the interval from 0 to pi? That's going to be at a 60-degree angle. Cosine's positive, so that's in quadrant 1. My theta value is going to be pi over 3. Okay. So to fully evaluate tangent of our cosine of a half, this is the same thing as evaluating tangent of pi over 3. And then we can go back and we can use our unit circle. That's sine of pi over 3 over cosine of pi over 3. You can use your chart too. This ends up being root 3. Let's try another one of these. We'll make it more complicated now. We've got sine of tan inverse of 3/2. So this one's a little bit different because I don't have a ratio I've seen before, 3 over 2. But if I go to evaluate this, it's going to give me some angle where this angle is in the interval negative pi over 2 to pi over 2. So this is the same thing as saying tangent of theta is going to be 3/2. Okay. So I'm going to need to create a triangle for this in order to evaluate sine of this angle. So if I've got my triangle going on, here's my right angle, here is my theta value. Because tangent's positive and this is quadrant 1 or quadrant 4, immediately I know this is going to be in quadrant 1. Okay. So this is y over x, and I know this is going to be in quadrant 1. Since tangent is positive. Okay. So my y value is 3, my x value is 2. I then need to figure out what my hypotenuse is. So my hypotenuse squared is equal to 2 squared plus 3 squared. That gives us 4 plus 9. So my hypotenuse squared is 13, meaning my hypotenuse is going to be square root of 13. So again, we always consider the hypotenuse to be positive. So to find sine of tan inverse of 3 over 2, I know tan inverse is going to be an angle. So this is really asking what is sine of that same angle. So using my triangle, sine is, using our SOHCAHTOA, it's the opposite over the hypotenuse. So sine of theta is going to be 3 over the square root of 13. And then again, we really don't like it with a radical in the bottom, so we times that by root 13 over root 13 to rationalize it. So sine of theta will end up being 3 root 13 over 13. Okay. If this was negative, that would just tell you because of the output of the tangent function, that would be instead in quadrant 4. So your x would be positive, but your y value would be negative. And so if you were finding sine of that angle, it would instead be negative 3 over root 13. Okay. All right, so I really have just one more left of working with this. And it's really a similar example to this last one, except instead of having a number on the inside, I've got an expression involving u. So ultimately, I want to figure out what does this equal in terms of u. So if I start with that inside, sine inverse of this expression, this gives me some angle, okay? And that angle is in quadrant 1 or in quadrant 4, okay? Again, we're going to assume everything works out nicely. We just want to write this in terms of u. This is the same thing as saying then sine of theta is going to be u over the square root of u squared plus 16. Well, if you think of your sine function, again, that is the opposite over the hypotenuse. So I'm going to use a triangle to figure out what this looks like in terms of u. Okay. So if this is my theta, my opposite side is u, my hypotenuse is u squared plus 16. Okay. This inside again is just going to be the angle theta. So if I want cosine of theta, I need my adjacent side over the hypotenuse. So I just need to figure out what does x equal, okay? So using our Pythagorean theorem, x squared plus u squared is going to equal the square root of u squared plus 16 squared. And I want to solve for x in terms of u. Thankfully, at least those square and square roots cancel. And then if I move this u squared to the other side, that gives me x squared is equal to 16. Okay. So we're going to assume the x value is positive. Just to make life easier, my x is going to equal 4. Okay. So if I want to now find cosine of this same angle that this ratio was 4, I'm just going to use adjacent over hypotenuse. Okay? So cosine of sine inverse of u over the square root of u squared plus 16 is the same thing as asking what is cosine of that same angle, which is my adjacent over my hypotenuse. Okay. So we're just using that triangle to figure everything out, okay? So again, these inverse trig functions are very important, and being able to figure out the angles that solve equations is essential. That is really what our entire next section is about. We're going to do tons and tons of trig equations. So I'm going to have to figure out what theta value makes it true. It might be on a specific interval. It might be over all the interval, the entire interval.